All right, guys, we're going to start this homework number 1 for second semester. First problem says find the distance between the points using the distance formula and then integration. If we're just doing 2 points, we don't really need calculus for this. The distance formula is the square root of. You're subtracting the x's and squaring them, and subtracting the y's and squaring them. Remember, this is also just Pythagorean theorem. So that distance should be, let's see, square root of 64 plus, what's that, 225. And that's the square root of 289, which is a perfect square, so the distance is 17. Again, it's also just a Pythagorean triple, so if you were to think about plotting these points, you're just finding the hypotenuse. So there's the distance there. But we did learn the arc length formula, right? So to use the arc length formula, remember arc length is the integral from a to b of the square root of 1 plus dy dx squared. And so we need to have a y so that we can have a dy dx. So I needed an equation of a line that passes between these 2 points. So if you just think about that, the slope of this line would be 15 over 0 minus 8 over 0. This goes through 0, 0. So the original line that passes through these 2 points would just be y equals 15/8 x, right? Because that goes through the origin and it has the correct slope. That allows me to find dy dx. dy dx is just 15/8, or I guess I could have just gone right there, right? Because I'm saying slope of a line. But anyway, dy dx is 15/8. I need dy dx squared in this equation. So if I want to find the distance between these 2 points, even though it's not a curved arc length works whether you have a curved function or a linear function. So this would be the integral from, excuse me, we're using x values here. So it would be 0 to 8. I know I'm using x values, by the way, because the original equation was a function of x. And so this would be the square root of 1 plus 15/8 squared. So let's just make that 225 over 64. Remember to put in your extra dx that's outside of the square root for this equation. And then this again would be, let's see, so this would be 64 over 64 plus 225 over 64. So this is going to be the integral from 0 to 8 of the square root of 289 over 64, if I get my common denominator. And I know this answer is going to be 17, but just to do the math behind this. So this is the integral from 0 to 8 of 17 over 8. And then if I integrate that, that's 17 over 8 times x. And we're going from 8 to 0. And yeah, we're going to get 17/8 times 8, so 17, minus 17/8 times 0. So you get 17 again. I think on my key I just said, yeah, okay, this is going to be 17. But that would be the math behind it. Okay, next one, find the arc length of the graph of the function over the indicated integral. So they give us the equation. We are looking at the integral from 0 to 1. So remember, I like to do some of the math before I set up the integral so that I'm not doing it all within the integral. So for our arc length formula, we need dy dx to begin with. So I need to take the derivative of this equation. So 2/3 times power rule to begin with, 3/2 times this quantity to the 3/2 minus 1. So 3/2 minus 2/2 is 1/2 power now. And remember, there's chain rule happening. We need the derivative of x squared plus 1, so times 2x. So let's clean this up a bit. 2/3 times 3/2 just cancels. So this is just 2x times square root of x squared plus 1. So that's dy dx. And then for the formula, we need dy dx squared. So I like to square this out here too, might as well. Remember, when you're squaring a product, you square both pieces of the product, so both factors. So 2x squared becomes 4x squared, and it gets multiplied by the quantity x squared plus 1 because we squared the square root. And I'm going to distribute that through as well when I put it into my formula. So now I'm going to go ahead and switch over to arc length formula. So the arc length is the integral from 0 to 1, those are the x values, of the square root of 1 plus, if I distribute this through, I get 4x to the fourth plus 4x squared. Now I'm going to do this homework assignment. This video is going to be pretty long because I'm going to do all of these without a calculator as much as I can. And that's not to say you won't have a calculator on the AP test, but the types of things, the types of non-calculator problems you see are going to be kind of the same process over and over. So when you have a polynomial like this, it should always work out, if we're doing something without a calculator, it should work out that this is a perfect square trinomial that we can factor and then take the square root of. So I'm going to do that here. And even if you did the 1 plus, you could also do the 1 plus dy dx squared work out here, all without the integral if you wanted to. But 4x to the fourth plus 4x squared plus 1 factors into a perfect square trinomial, 2x squared plus 1, the quantity squared. So when we square root 2x squared plus 1 squared, that's going to take away the square root part. So now it is just the integral from 0 to 1 of 2x squared plus 1 dx. And that is something we can integrate just using our little power rule here. So x squared becomes x to the third over 3. So 2x to the third over 3. 1 becomes plus x. Evaluate from 0 to 1. And so that is going to be, if I plug 1 in, I get 2/3 plus 1. Minus, if I plug 0 in, I just like to consider that in case there's a non-zero term. So 2/3 plus 1 is 5/3. If you did this on your calculator, that's about, it would be approximately 1.667. So same idea. All right, so take a look at 5. 5 looks like almost the same equation. We just have the 3 halves is on the outside of parentheses, and here it's just on the x. So this is a slightly different problem. So let's see. For number 5, I'm going to start off the same way, where I need to have a dy dx. This is a bit shorter, right? So the power rule here makes this 2/3 times 3 halves x to the 1/2. And then the derivative of 1 is 0. So this is nice. Dy dx is just x to the 1/2, or square root of x. And then that's pretty good because, sorry, I was getting distracted for a moment. So that's good because if we square that, that just becomes x. That's nice and easy. And then if we put this into our arc length formula, it will be the integral from 0 to 1 of the square root of 1 plus x dx. All right, now remember, we've done a lot of integration up to this point, so it's kind of like, oh wait, this isn't something I can factor. But remember, this is like a little u sub, although u sub is not really necessary because u would be 1 plus x. Du dx would just be 1. So there's not anything I need to fix to make u sub work, but still, it's just a square root. It's the integral from 0 to 1 of just square root of u du. Okay, so how do you integrate that? So that's u to the 1/2. So when you add 1 to 1/2, you get u to the 3 halves, but let's switch the u out. Divided by 3 halves or times 2/3. Evaluate this from 0 to 1. So if I plug 1 in, I get 2 times 1 plus 1 is 2 to the 3 halves over 3. And if I plug 0 in, it's not 0, it's 2 times 1 to the 3 halves over 3. So let's add our exponents here. 2 to the first times 2 to the 3 halves is 2 to the 5 halves over 3 minus just 2 over 3. And I think that I'm just going to leave my answer like that. I guess 2 to the 5 halves, let's see, we could work on that, right? 2 to the 5 halves, that's the square root of 2 to the 5th. 2 to the 5th is 32. And that's 16 times 2, so 4 radical 2. So I guess you could make it like 4 radical 2 minus 2 over 3. It doesn't matter if it's a free response question, whether you simplify it or not, but if you're looking for, this will more likely be something multiple choice. So they would probably have their answer in this form, I would guess. All right. Let's see, number 7. So we still want arc length for this one. So I'm going to start with dy dx. So that becomes 3 halves times 2 thirds times x to the negative 1 third when we subtract 1 from that. So dy dx is x to the negative 1 third. And if you square that, you get x to the negative 2 thirds, which is actually 1 over x to the 2 thirds. When we're working with, since I'm going to be adding 1 to this, I want to get rid of my negative exponents anytime I'm doing algebraic operations. All right, so when I put this into my arc length formula, it's the integral from 1 to 8 of the square root of 1 plus 1 over x to the 2 thirds dx. And in this case, we always get a common denominator. So this becomes the square root of x to the 2 thirds plus 1 all over x to the 2 thirds dx. Remember, the next step is usually to square root things. I can't square root the top. I can't factor that nicely, but I can square root the denominator. So let's go ahead and do that. So this is going to remain the square root of x to the 2 thirds plus 1. The square root of x to the 2 thirds, remember, I squared x to the 1 third to get that, or if you want to square root x to the 2 thirds, remember that's the same as raising it to the 1/2 power. I think sometimes that helps us, like we're just multiplying 2 thirds times 1/2, so you're left with x to the 1 third. If you're having a hard time thinking about that square root. All right, and then what do we do here, because we still seem kind of stuck. So again, don't forget about our main options. So when we have something ugly and it's not an obvious like inverse trig or something like that, always think about u sub. So I'm going to let u equal the expression underneath the radical. Let's see if this works. X to the 2 thirds plus 1. And then du dx would be 2 thirds x to the 1 third plus 0. And that means that, let's see, du, oh wait, no, not x to the 1 third, x to the negative 1 third. That's important. I was pausing because I thought, wait a minute, I'm not going to have this cancel. So if I solve this for du, I'm going to multiply by 3 halves, and then this x to the negative 1 third is down in the denominator, so it would multiply up here, x to the 1 third times du, and that would equal dx. And so if we look at what's going to cancel, so instead of dx, we have 3 halves x to the 1 third du. So yeah, those are going to cancel. So we're going to have 3 halves, which I'm pulling out, times the integral from 1 to 8, and now it's just square root of u du. And we can integrate that and replace our u. So u to the 1/2 becomes u to the 3 halves times 2 thirds. And instead of u, I'm going to put this back in. Remember, you do have the option of solving these x values for u so that you don't have to do the substitution. The amount of math you do is the same, so it doesn't matter. Also, if we have a constant here, we can pull the 2 thirds out. So the 3 halves and the 2 thirds can just be canceling out. All right, so really it's, okay, this is going to be 8 to the 2 thirds plus 1 to the 3 halves power minus 1 to the 2 thirds, so that's just 1, plus 1 to the 3 halves power. So what is 8 to the 2 thirds? So that's the cube root of 8, which is 2, squared, which is 4. So this is 5 to the 3 halves, which does not simplify nicely. Square root of 5. I guess I can simplify radicals, but whatever. And then this is 2 to the 3 halves. It's not the same as 5 minus 2 to the 3 halves. You can't you can't like merge them under the same radical. So all you can do with this is leave it as it is, or you could make this like, what would this be, like 5 radical 5 minus 2 radical 2, I guess. But I guess I'll do that. 5 radical 5 minus 2 radical 2. Or again, you could get to a decimal approximation. If you're allowed to use a calculator, you don't do any of this. You pop this thing into your calculator way back here and call it a day. All right, for number 9, same thing as arc length. So dy dx is equal to, so this is going to be 5x to the 4th over 10. And then this is really 1/6 x to the negative 3rd, right? Yes. So then that's going to be negative 3 over 6. And then x will be to the negative 4th. So I'm going to put x to the 4th down here. Because we want to square dy dx, we should get this into a single fraction first, and we should simplify things. This is just x to the 4th over 2 minus 1 over 2x to the 4th. So the common denominator is 2x to the 4th. The first fraction needs to get multiplied by x to the 4th, so that becomes x to the 8th. Second fraction needs nothing, so minus 1. So this is my simplified dy dx, and then I need to square this. Now when I square it, remember, most often when we have these polynomials and we're working with arc length, we're going to have a perfect square trinomial somewhere. So I do need to square out x to the 8th minus 1. So if I square that out, x to the 8th minus x to the 8th is x to the 16th. You're going to have minus 2x to the 8th and then plus 1. So that's just me squaring that binomial. And when you square this denominator, you get 4x to the 8th. Right? And then we're going to put this into our arc length formula. How much room do I have? Oh, I have room. Okay, so arc length formula is the integral from, it tells me to go 2 to 5 of the square root of 1 plus all of this. And again, this wouldn't be unheard of, that this could be a non-calculator, like multiple choice problem. So even though it's kind of tedious and it's a lot to get through, the steps are always the same. So once we get all of this out, you need to do a common denominator here. So 1 is going to be 4x to the 8th over 4x to the 8th. And when you add your numerator terms together, that's going to make this something I can factor. So let's clean this up a bit. So we have the square root of, make that a bigger square root, x to the 16th. 4x to the 8th minus 2x to the 8th is plus 2x to the 8th plus 1. And then down here it's 4x to the 8th dx. Now we can square root both parts. This is x to the 8th plus 1, the quantity squared. So when I square root that, I'm going to get x to the 8th plus 1. And then when I square root 4x to the 8th, I'm going to get 2x to the 4th dx. Okay, and then what are we looking at for integration here? For this one, remember it's a binomial divided by a monomial. So we should just be dividing, right? Like boop, boop. So clean this up a bit so that you're not using, I don't know, u sub or something like that. That wouldn't even work. So when you divide the first term, this becomes, we can just pull a 1/2 out. Well, no, I want to do them both. Okay. I don't like pulling a 1/2 out because I feel like I'm going to mess it up with my addition in there. So, okay, so this is going to be x to the 4th over 2 plus 1 over 2x to the 4th dx. Now we use a little bit of power rule here with integration. So this becomes x to the 5th over 5 times 2, so over 10. And then this is 1/2, this is 1/2 x to the negative 4. So that becomes 1/2 x to the negative 3 divided by negative 3. So minus 1/6 x to the 3rd down there. going from 2 to 5. And now we should be able to plug numbers into this. Let's see. You know what? We could probably, now would be a good time to factor out the 1/2 so we don't have as large of numbers maybe. I don't know. Does that matter? Probably not. I might just be doing extra work here. I'm trying to make it match a little bit what I did with my key though that I posted. Okay, so let's plug in the numbers here. So we get 1/2, and then what do we have when we plug stuff in? So 5 to the 5th, whatever that is, over 5, minus 1 over 3 times 5 to the 3rd, minus quantity 2 to the 5th, okay, I know that one, over 5, minus 1 over 2 times 2 to the 3rd. And I did not simplify this very much on my, on my answer key. This is a 3 down here, not 2. So I don't think I'm going to take the time to simplify it from there. I'd be surprised if we were working with these fractions on a non-calc, not because we can't do it, it's just that it's time consuming. So I'm going to stop this one there. And I guess I'll circle, or I'll box that in as my answer. All right, for number 11, y is the natural log of sine x. We're on this interval. And I have a note that I pulled from the earlier, this was like somewhere in our chapter 4 notes, I think. So we're going to be using this. But let's just see. First off, we need dy dx. The derivative of a natural log is 1 over the thing in the natural log times the derivative of that thing. So derivative of sine is cosine. And that means that dy dx is actually just cotangent x. And we're going to have cotangent squared. So dy dx squared will be cotangent squared x. And arc length will be the integral from pi over 4 to 3 pi over 4 of the square root of 1 plus cotangent squared x dx. This should be setting off alarm bells in your head from pre-calc last year. This is one of our Pythagorean identities. Of all the identities we need to know reciprocal, quotient, Pythagorean for calculus. So 1 plus cotangent squared is equal to cosecant squared. Remember, 1 plus tangent squared is secant squared. 1 plus cotangent squared is cosecant squared. So that's good because that means that we can, if this is cosecant squared x, we can square root that. All right, so really this is just cosecant x dx, which brings me to this. Remember, we can't just do a nice, easy u sub to figure out what the integral of cosecant is. We can we know sine and cosine. We can do a quick and easy u sub for tangent and cotangent. But I tried working on this with cosecant and secant, and it was definitely a long, drawn-out thing with lots of magic and things you have to do to get there. So I haven't had to use this on an AP test yet, but, you know, I don't know. I can't guarantee that you won't have to do it. But anyway, here we go. So what's the rule here? So this is, the answer here is going to be the negative natural log of the absolute value of cosecant. It says u, but we just have an x, so we don't have to think about u sub there. So cosecant x plus cotangent x. And we're evaluating that from pi over 4 to 3 pi over 4. And now we just have to plug stuff in. So negative natural log of cosecant of 3 pi over 4. So remember, you have to consider sines and stuff. So all students take calculus. Okay, so sine and cosecant at 3 pi over 4 is over here in quadrant 2. So they're positive. Now remember, sine and cosine are radical 2 over 2, but the reciprocal of radical 2 over 2 is radical 2. That scared me. And then cotangent. Cotangent of 3 pi over 4 is negative 1. Now, I don't really need this absolute value because radical 2 is 1 point something. And so that's going to be a positive difference, but it doesn't matter. You can leave it. And then minus negative, so plus natural log of. When I plug in pi over 4, I also get radical 2, and then this is going to be plus 1. Now, you might find that this answer in multiple choice has been condensed. So remember, we can condense this natural log, and because the negative is in front of the first natural log, that expression would go in the denominator. So it would be like the square root of 2 plus 1 over the square root of 2 minus 1. That would be my solution that I was looking for. All right, for number 13, still doing arc length. All right, so dy dx is equal to 1/2 times, so what's the derivative of e to the x? E to the x, plus the derivative of e to the negative x, so that's negative e to the negative x. Because you're going to be squaring this, it would be a good idea to get rid of the negative and do a common denominator thing. So just work on this a bit. So I'm going to keep the 1/2 out here. This is e to the x minus 1 over e to the x. So e to the x up here needs to get multiplied by another e to the x. So that's going to make it e to the 2x minus 1 so that it can all be over e to the x. And then we might as well merge this together. So e to the 2x minus 1 over 2 e to the x. That's dy dx. Now we need to square that. I should have said this earlier, but make sure you're not writing down false equivalencies. It would be wrong to write just equals and then square this because then you're saying that that's still equal to dy dx. So you should write, when you're doing a new thing, you should write what the new thing is. So dy dx squared equals. So I need to square this out. Remember, we do that with when we have something that we're probably going to factor. So this becomes e to the 4x minus 2 e to the 2x plus 1. And then when you square this, you get 4 e to the 2x. And then into the arc length formula. So the arc length is the integral from 0 to 2 of the square root of 1 plus all of this. So this should look familiar. We did this in a previous problem. It just wasn't in terms of e. Steps are going to be the same. So once I set this up, I want to get a common denominator. So 1 is going to become 4e to the 2x over 4e to the 2x. I'm being a little bit lazy and not rewriting every single step, which I think is okay. That gives me the square root of e to the 4x, and then 4e to the 2x minus 2e to the 2x gives you plus 2e to the 2x plus 1, and it's all over 4e to the 2x. The point of doing all that is that this trinomial up here is a perfect square trinomial. It's e to the 2x plus 1, the quantity squared, and 4e to the 2x is also a perfect square. So we can square root this whole fraction. So this becomes e to the 2x plus 1 because I took the square root of something squared. And then this becomes 2e to the x. All right, and now can we integrate that? Let's pull there's a 2 in the denominator. Let's make that a 1/2 that we pull out. And we're going to do the same thing we did in the last problem, or maybe it was 2 problems ago, where we go ahead and divide this out. This time I am pulling the 1/2 out, so let's see if I can do this correctly. So e to the 2x divided by e to the x, you subtract your x's and you're left with e to the x. And then it would be plus 1 over e to the x, or let's just write that as e to the negative x. And I already pulled the 1/2 out in front. I don't know if you can hear my clock on the video dinging, but anyway. Okay, so then we need to integrate this. Now, we do have to be careful. There's a little bit of u sub that we're going to have to use here. So we need to be very mindful on how we're doing this. And actually, because I don't want to screw up a negative sign or something and go through all this work just to have that little negative sign mess me up, I am going to take the time to rewrite this integral separately. So 1/2 integral from 0 to 2 e to the x dx. That's easy. Plus 1/2 integral 0 to 2 e to the negative x dx. So remember, you need to account for the negative inside of the function. So u is negative x, du dx is negative 1. So negative du is equal to dx. So instead of dx, I really have negative du. That means this is going to become a minus right here. So we have 1/2 times e to the x evaluated from 0 to 2. And then it's going to be minus 1/2. So I've got the minus in there. Oh, that should say minus 1/2. Sorry, not minus 1 over 0. Minus 1/2. There we go. E to the u, or e to the negative x, evaluated from 0 to 2. All right, so that minus I just put in there, and then I just went ahead and integrated because this is still integral of e to the u, and want to rewrite that. Now we have to integrate, or evaluate. So 1/2 e squared minus, remember, e to the 0 is not 0, it's 1. So make sure that you are plugging 0 in. Minus 1/2 1 over e squared minus 1 over e to the 0, or minus 1. And let's see, that's going to be, so this is 1/2 e squared minus 1/2 minus 1/2, oh no, not minus 1/2 e squared, minus 1 over 2 e squared plus 1/2. So the 1/2's cancel. So be careful how you write this. I've been kind of sloppy here. E squared over 2 minus 1 over 2 e squared. Or get a common denominator if you want to. All right. I just, the way I wrote this is kind of misleading and not obvious to say that e squared is not in the denominator. I should have done something like this. All right, number 15. This is a long assignment because I'm going through all this non-calculator, but anyway, if you get the idea, you can go ahead and set these up with your calculator too if you want to. Now this one is a function of x in terms of y, or a function of y, I guess I should say. The process is still the same. It's just we need dx dy instead of dy dx. We're taking the derivative with respect to y of both sides. The bounds are in terms of y, so that's why I'm keeping it like that. And when I when I solve for that, pen just died. When I solve for that, I get 1/3 times 3/2 times y squared plus 2 to the 1/2, because I subtracted 1 from my exponent. And remember to chain rule. This is kind of like the first problem we did. It's just switched around, the inverse or something, or not the inverse. They just switched x and y. Okay, and then let's see. So the derivative of y squared plus 2 is 2y. Cleaning this up, the 3's cancel. This 2 cancels with this 2. So I really have dx dy is equal to y times y squared plus 2 to the 1/2. And dx dy squared will be y squared times this quantity y squared plus 2. Now it's to the first power, which is y to the 4th plus 2y squared. And you can see that's part of a trinomial that we're going to be able to factor pretty soon. So the arc length will be the integral from 0 to 4 of the square root of 1 plus y to the 4th plus 2y squared dy. This is a perfect square trinomial again. It's y squared plus 1 squared. So now it's the integral from 0 to 4 of y squared plus 1 dy, because I took the square root of a perfect square. And that gets me y to the 3rd over 3 plus y from 0 to 4. And that gets me 64 over 3 plus 4 minus 0. And that gets me 76 over 3. And does that go in nicely? I don't think so, no. 76 over 3. Because 7 plus 6 is 13, and that's not a number divisible by 3. So, yeah, no. Okay, that was a long slog here. Let's see what these are. Looks like I'm using calculator for these. Okay, part A. Sketch the graph of the function. Oh, I left my sketch on here, so Yeah, just be able to sketch these graphs. I did not use a calculator. You should be able to sketch these without a calculator. You need to know the shapes of these functions. Okay, anyway, sketch the graph for part A, done. Highlight the interval indicated. I tried to do that in a different color. B, find a definite integral that represents the arc length of the curve over the indicated interval, and observe that the interval cannot be evaluated with techniques studied so far. So in comes our calculator. Use integration to approximate the arc length. Okay, so we're going to begin with, we have y. What's dy dx? So dy dx is 0 and then minus 2x. Dy dx squared is 4x squared. The arc length would be the integral from 0 to 2 of the square root of 1 plus 4x squared dx. Now, u sub wouldn't work here because du would still have an x in it and there's no x to cancel out. This isn't anything I can factor, and I can't square root terms individually. So yes, we are stuck there. So then we just hop over to our calculator and see what the arc length comes out to. So remember, anytime you're allowed to use a calculator, you do not have to go through, not that there's algebra to do, but you don't have to go through all of the painstaking algebra that we were doing to get to the final answer. As soon as you get 1 plus whatever dy dx squared would be, whether you simplify it or not, or just put it in parentheses, you should be able to find the arc length right away. So 4.647. Let me write S. So S is approximately equal to 4.647. Okay, and I left my answer up for the rest of these because, just again, I know this was going to be a long video, so I'm not going to take the time to type it up every time. All right, so what about this one? So I've sketched the 1 over x graph. We're looking at the interval 1 to 3. So dy dx, this is x to the negative 1, so it becomes negative 1 over x squared. Dy dx squared becomes positive 1 over x to the 4th. And the arc length would be the integral from 1 to 3 of the square root of 1 plus 1 over x to the 4th dx. Even if you work on this a bit, which is what we normally do, we can get it to be x to the 4th plus 1 over x to the 4th. But the problem is that even though you can square root the denominator, you cannot square root the numerator. And then u sub's not going to work, which would be the only other option that we have. So u sub doesn't work when there's more than a 1 degree difference between what you're using for u and what else is left outside of the function. Like we'd have an x squared instead of an x cubed. And then this was the answer I got when I typed that in. All right, the sine graph, think back to your trig days here. So we're looking at 0 to pi. So we should know that sine starts at 0, 0 and goes up to 1, comes back to 0 at pi, goes down to negative 1, hits 0 again at 2 pi, but we're only looking at this little 0 to pi hump. So dy dx is equal to cosine x. If I put this in the arc length formula, I get this integral from 0 to pi of 1 plus cosine squared x dx. And 1 plus cosine squared is not anything. 1 minus cosine squared would be sine squared, but 1 plus is nothing. And that's nothing I can use for u sub either. So using a calculator, I would go back up here. All right, for number 23, here's e to the negative y. Oh, wait, did I actually do? Hold on. I don't think I graphed that correctly. I just now caught this, like, oh, e to the negative y. That would be like if this was the y-axis and this was the x-axis. I don't think I did that correctly. I'm going to fix this. How do I know what that looks like? I didn't catch this while I was doing it. But what I should really do is natural log both sides. It's actually the natural log of x. Maybe that was right. Equals negative y. Negative natural log of x equals y. So maybe I did inadvertently sketch this correctly. The natural log of x has a vertical asymptote here. At 1, it hits 0. it's an x-axis reflection, so it does one of these. Okay, so I guess maybe it was okay, but the y values we're looking at go from 0 to 2, so maybe it was fine. But that just, I don't think I considered that. I think I just, oh no, I did, because I didn't do a negative. That's not a negative, e to the negative y. Okay, never mind. Anyway, to graph this, that's what you would have to do to graph this, because we're used to graphing in terms of x, not in terms of y. And now that I look at my answer key, yeah, I did have that done correctly. So that's okay. Anyway, part B. So let's see. We're going back to, because the equation is in terms of x, we're going back to dx dy. And because the bounds are in terms of y. There's no need to complicate it and switch everything around. Dx dy is equal to negative e to the negative y. Squaring dx dy, I get positive e to the negative 2y. And the arc length would be the integral from 0 to 2 of the square root of 1 plus 1 over e to the 2y dy. And I'm going to run into the same thing I did back here, where even if I get a common denominator, it's not going to give me anything I can factor. All right, the arctangent graph. You need to know the arctangent graph, which shape it goes. It's, I just always kind of remember that it is up and to the right. Now this one's 2 arctangent, so normally there's a horizontal asymptote at pi over 2, but this time there's going to be a horizontal asymptote at 2 times pi over 2, or at pi, but I didn't sketch that in here. All right, so dy dx is 2 times, what is the derivative of arctangent? Remember, we had 2 ways to think of this. One was like drawing a triangle, which is kind of tedious. But remember, we're used to looking for the integral. The derivative of arctangent u, is u prime over 1 plus u squared. So u is just x, so we kind of got lucky here. So the derivative of x is 1 over 1 plus x squared. So that's pretty easy, right? And then if you want to square that, dy dx squared would be 4 over x to the 4th plus 2x squared plus 1. And the arc length would be the integral from 0 to 1 of the square root of 1 plus 4 over x to the 4th plus 2x squared plus 1 dx. And if I get a common denominator on this one, I'm thinking it's probably not a perfect square trinomial, right? It would become, because all of this would be here, you would get like x to the 4th plus 2x squared plus 1 plus 4, so plus 5, and that doesn't factor. Okay, so that's not going to be something we can work with, so we go back to our calculator for that. Okay, final problem, and it's multiple choice. And actually, I think this is not that easy of a multiple choice, but that's okay. Determine which value best approximates the length of the arc represented by the integral. Make your selection on the basis of a sketch of the arc and not by performing any calculations. So I think what they mean is like, don't just find the arc length of the thing. Okay, so what does that mean? Well, they're showing you the function right here, 5 over x squared plus 1. So they're showing us that function, and we're going from 0 to 2. So let's go ahead and sketch the arc. Now that I'm looking at my answer key, I sketched the derivative, but that was kind of silly. I think I should have, I want to do it this way. So let's see. So let's sketch 5 over x squared plus 1. We're on 0 to 2. So if you plug 0 into that, you get 5. If you plug 2 into that, you get 5 over 4 plus 1. 5 over 5 is 1. And that would be some sort of like, I don't know, curve like that. So even though we're not supposed to perform calculations like calculus calculations, I think that it's fair to look at this as a triangle. I think I could say, okay, I've got one leg that's 4. I've got one leg that's 2. And I could see if it's reasonable to say that the third leg, let's see, the third leg would have to be bigger than 2 and bigger than 4. So negative's out, 25 is too big, 2's out. I think it's got to be 5, except if I remember correctly, the book said 3. And maybe if I do actually integrate here, maybe I've miscalculated something somewhere. Have I? Looking at the actual arc length from that to that. I wonder if there's like more of a curve than I'm thinking of with what this would be. I was just going off of this, like what that would be. So in my original answer key, I had 5. In my final one, I had 3. Because, okay, here's what else I was doing. I was saying, what is the derivative of 5? Let's go through what this would be. And actually, let's see. So 5 times, how did I just say that y was equal to? Yeah, I was looking at on my answer key that I posted. I think I was thinking about it wrong. I did come to the 3 conclusion, which is what the back of the book said. I'm going to need to think on this one more. If any of you have any insight to this as to why it wouldn't be 5, why it would be 3, let me know. We might as well graph this. Let's see what this looks like. 5 over x squared plus 1. Let's just look from 0 to 2. Yeah, I don't think that's that crazy to say. This leg's 4, this leg's 2. The triangle isn't going to have a hypotenuse of 3, but maybe it's because 5 would be an overestimate. Maybe that's it. Like 5 would be maybe, I don't know. I don't know. We're coming back to this one. My video is already way too long, I'm sure. So we can talk more about this in class if you want, or if any of you want to investigate it further, do that. Okay, my last thing. I do want to look at what, I know it said don't do calculus, but I'm doing calculus because I want to see. Let's see. Now this would be this derivative here, because I don't want to type in a derivative into my calculator. The derivative of this. Oh, yeah. And see, that's not arctangent. Why was I doing that? I don't know. Anyway, x squared plus 1 to the negative 1. It's negative 5 over x squared plus 1 squared. And then you're squaring that quantity. 4th. Let's see what this comes out with. X squared plus 1 to the 4th. If this gives me something crazy, I'm just going to call it a day. It's a snow day anyway today. We're doing too much work. See, I got 5. Okay, maybe the back of the book's wrong. This is awfully close to 5 if we actually do the math on that. I'm going with it. 5, and I'm updating my answer key. Okay. Thanks for sticking with me. If you sat through this whole video, hopefully you skipped around and found the part you needed. I will see you tomorrow, I think. We've had a lot of snow days.